Okay, so
There is no limits.
the concept is quite simple. Let's say we have a curve. Some curves, not a problem necessarily. We know we can find the derivative and take or draw tangent lines at points that we need. Yes, we've done that. That's pretty much what we mean by a tangent line. And since the beginning of chapter 3, you guys did all kinds of problems in web design, find the equation of the tangent line at this point, that point, this point. So, why did we do that? Hypothetically, imagine that these are tangent lines, the ones that I'm about to draw. Obviously, it's not going to be great. Yes. Infinitely many tangent lines. So if I simply picked a few of them into the infinitely many, I could create something like this. Yes. Using those lines. Hypothetical. What is the difference between this and this? Oh,
That's just made up of tangent lines.
that's made up of tangent lines. Okay, what else?
Constant for
It is constant for each period in terms of looks.
Did you say looks?
Yeah.
Wow.
Looks are quite important here.
Wait, did you say looks are or aren't?
Oh,
Oh. Oh, I mean overall.
Louis, let's ask more points. Okay, what else? So this curve, when I first drew simple orange line, it was a nice little curve. That's a curve with makeup. This is without makeup. Good. So that's an estimate. This is an exact curve.
Models with
So-
Photoshop and models.
Exactly. With filter, without filter. Instagram. Instagram. Moving on. So all I'm doing is I'm using a bunch of lines to connect and form the outline of a curve. Why is this important? Because there are curves where you can't you can't come up with an exact curve form and expression. So we go for an approximation. Of course, if I use few of them, for instance, just 5 lines, I might get something like that. Is that great? No, not even very close. But the more points that I use, the better the approximation is going to. So linearization simply means you take a function and you express it in a bunch of lines. But the only issue here is you have to approximate at multiple values. Reason being, suppose I have a point A. So I can approximate this value right there pretty much nicely with a derivative, a tangent line. But the tangent line has the same slope for a tiny bit over here, yes, on a short or a small interval. But as it goes up this way and that way, it is going to depart from the curve. Yes, it's going to go farther and farther away. So whatever approximation that you make at that point is a good approximation as long as you are very close to A. By very close, I mean very close. 0.1, 0.01. Of course, it would depend on the curve that we're dealing with. So if I pick multiple a's, I can simply approximate the values around those a's, every single one of them, to get approximations on anything. Does that make sense? So that's what we call refinement of an approximation. So you go from few points over there, increase the number of points of approximation, gets better, increase a bit more, it gets better. But eventually, no matter how hard you try, you cannot get the exact curve. At the end of the day, it would still be an approximation. Does that make sense? The only way you would get an exact curve is if you pick infinitely many points. But do we really want to do that? It's not feasible. So, are we clear? So what we're going to do is that we're going to approximate points on a curve using a tangent line. The key thing to remember is that approximation will hold true in a neighborhood of the value where you approximate. Good. I'm going to erase this. That is my function f of x. Good. And f prime of x would be the derivative. Do you agree? But f prime of x is approximately equal to the average rate of change. Do you agree? As long as the interval is very small, it is simply the average rate of change. So we are going to pick a point very close to point A. So this is f prime of A. The derivative at the point A, because that's what's going to approximate our function at the value A. So pick a point very close to x, excuse me, very close to A. I can find the slope, correct, average rate of change. So I've got A, I've got x. What is the denominator? x2 minus x1, so it has to be change in x, yes, in terms of x and a. It would be x minus a. Good. In the numerator, what would we have? y2, go ahead, Caitlin.
F of x minus f of a.
F of x minus f of a. Good. So what I'm trying to say is show I can find the derivative of a function if I pick a point very close to A. The derivative, which is the instantaneous rate of change, would be very close to the average rate of change because I'm very close to the point A. If I did some algebra, multiply both sides by x minus a, I would end up getting f of x minus f of a.
So, sir, I'm reusing this at the very least. Would it be, let's say that we had
a problem where to find the derivative would be going through a lot of slog and such like that. We only needed a numerical value, as in the slope of the tangential line. Because of that, we could then use this, correct?
Yes,
That's the point of this.
correct.
Okay.
We're trying to come up with an approximate. So f of x would then be, if I move this to the other side, I would have f of a plus f prime of a multiplied by x minus a. Good. With me so far. What does the left-hand side look like? I'll give you a hint. What?
I said that it looks like the y equals mx.
Y equals mx plus b. That's y m x and b. Correct. So we know f prime of a is simply the slope. X is just some point here. I'm just shifting it by a. And that would become the intercept b. So I have the original function represented as a line, hence linearization of a function in the neighborhood of a. Does that make sense? So since it is an approximation, your book calls it as L of x to denote a linear approximation. So that would be the final linear approximation. So I can keep on approximating really well as long as I'm close to A. What do we do if we want to approximate at a different A value? We'll keep changing the A values and coming up with lines time and time again to get a linearization on the entire domain. Good. Okay. So we want to come up with a linearization for this particular function.
So example is f(x).
At a equals -2. That is our function. It is a cubic polynomial. So the very first step that we have to do is to find the derivative. So what is f prime of x? 3x squared minus 2x. The next step is we want to find f prime of a. So I'm going to plug in -2. Three times -2 squared, -2 times -2. That is 4, 4 times 3 is 12. And -2 times -2, +4, we'll have 16.
And then we just need to do regular alphabet.
Yes. Now, we also want to find f of a. So we've got to plug in -2 in the original function. So f of a would be -2 cubed minus -2 squared plus 3. -2 cubed is -8. -2 squared is 4, and there is negative, so -4 plus 3. Good. And negative, excuse me, -8, -4, -12, +3, -9. Yes, that's the original value of the function.
So now we have that.
So the linearization for that function is simply f prime of a, which is 16, times x minus of -2, which is +2. Let me not skip a step. Plus f of a, which is f of -2, will have -9.
So L of x.
So the final answer (16x + 2 - 9). We can simplify this further. 16x, 16 + 2, excuse me, 16 times 2, 32, 32 - 9, 23. Now, do you see that mx plus b part? Okay. That is what we call the linearization. And we started by using the original function. If I plug in -2, exactly. So -2 over here, -2, I'm going to get the exact value of the function. Has to, right? Because we started with the exact value of the function. So the goal is to approximate in the neighborhood of a. Let's see, I'm going to pick a bunch of values.
So now we have to approximate x or x.
Yes. So we'll use table set. So -2, -2.01, -2.05, -2.1. Good. On this side, -1.99, -1.95, -1.9. This is what I'm going to do. I know the line version, yes, the linearization of the function. So use this line, different value of x, these values, and let's evaluate the approximation. And use another equation, plug in the function of x cubed minus x squared plus 3. Evaluate the function at each of those values, so we'll get values here as well. I picked them. So, and I'm going to say as to what I picked these numbers for later. But I picked those numbers.
Okay, yeah, so why exactly are we trying to approximate x when we could just do -2.000001 and that would be it? Because x only has to be a point close to a. What are we using x to, or why exactly are we considering x as so important that we try to approximate it to different degrees?
So this is the basic case, right? It might seem very trivial to you, but to me, it's very trivial also. In the sense, in the neighborhood of x, I'm trying to approximate it with the line. Here I have a nice little function, but what if you go to higher dimensions? Let's say you have two-dimensional surfaces, three-dimensional objects, and we use facial recognition and stuff, right? So a face, when you take a picture, it's a very pixelated, smooth version, right? But mathematically, you cannot take every single point to recognize that particular face. You need an approximation. How do you approximate? You would put a bunch of polygons and get a crude approximation of that face.
So the
Where does
approximation,
that concept come from? Here.
so the approximation would be, so let's say inside the facial recognition example. And I'm just saying this because a real world application would really help to, try to understand all that. When it comes down to it inside of this, they just think the average of all the values and they would get for here to be the approximation.
No. Each of these would be an approximation in the neighborhood of that function.
So what happens is that they have, let's say, a list of X values for this range to this range. See how they do, see if it somewhat matches one of these values or good.
Yes.
Oh,
Now, I am doing this to compare and show you how the approximations compare. In practice, we would only have the approximation. Let's say, what are the values that we got for the original function?
No, today, I was like.
Two decimal places, negative 10.67,
And that 5 minutes was all you.
negative 9.81,
Negative 9.16.
negative 9.16.
Negative 9.
So did not.
It has to be
Yeah, I looked at it
negative
6:15,
9.
6:20, I must have
Negative
checked.
8.84. Negative 8.2. Negative 7.46.
Okay, over here, two decimal places.
They don't give you.
Oh, okay. They gave you one decimal place.
Negative 10.6, negative 9.8, negative 9.16, negative 9, negative 8.84, negative 8.2, and negative 7.4.
Did the approximation do a good job? Yes. Yes. So it's not the exact value, but it is an approximation. So what we're trying to say is, instead of having infinitely many points, define this function between -2 and -2.01. I can just use these 6 points to approximate in the neighborhood. In practice, I don't even need 6 points. I could just go for 3 points and 2 points on each side. As you can see, the farther you go from the actual value -2, the less accurate it would become. So here it was quite perfect. There it was. Over here, the difference was 0.01 in terms of magnitude. There, it became 0.07 in terms of magnitude. 0.07 there, 0.06 here. So it will keep on increasing. I want you to pick, let's say, the number 4. No, not 4. Doesn't matter. -4. And plug it in the approximation, plug it in the original function, and tell me what you get. -4, the original function, -77, okay,
-41.
-41. Is it a good approximation? Absolutely not. Now, -41, -77, nowhere close. And why did it happen?
It's far away.
We went really far away from -2. So earlier I drew that tangent line. The tangent line is going to approximate things really well, as long as you are close to the point where you evaluate. The farther you go, the worse it's going to get. So -4 over the approximation, +4 over approximation. Good. There is a reason why I drew this curve. I wanted to know if my estimates are going to be overestimates or underestimates. It all depends on the shape of the curve. -2 is right over here. So if I drew a tangent line, that tangent line is going to go above the curve. Of course, it is going to definitely touch at that value, but in all other places, it is going to be an overestimate. So yes.
When it comes down to it though, you would have to move the x-axis up, considering that -2 is technically below the x-axis. -2 will go into a -1. Oh yeah, it would go into a -y. So it'd be like -11.
So like your point's just on.
Huh?
Your point's just on.
Oh, my point is off.
Yeah.
So where is it at?
It's actually at the bottom. And then
Yeah.
It's
It would be,
-9.
it would be -11 would be the y.
Oh, yeah, it's right over there.
Yeah,
Bad math. Okay.
just drawing.
Yeah, I was drawing a different graph entirely. So, regardless, so a poorly drawn tangent line, of course, your calculator is going to do a better job. I should have paid more attention. I have -2, -9 lines of it.
I mean, to be honest, we weren't even expecting really to have class today until a couple of days ago. So nobody can really blame you for being kind of off your game. Which is not to say that as an insult, but I just mean that you're
It's
human.
okay. I'll live for another day. -2, -9. So when I draw that tangent line, this tangent line is slightly above the curve. So as I go in the neighborhood, I'm going to sort of overestimate on this side. Same is going to happen over here, but when I move over to that point, for instance, something over there, the tangent line would be of that sort. And if I approximate in the neighborhood of that point, my estimates are going to be under. Good. So underestimation, overestimation. But we settle eventually as long as I'm in the neighborhood somewhere close to that -2. Good.
I was just curious why,
Okay, so
and then that gets close to 2, is that what it is?
that's -2, and that would be 1.1 instead.
Yeah, it's around that area.
1.1.
So that's basically you have the asymptote at -2, is that what that is, or it just gets really, really close? Oh, wait, it touches.
Not
Okay,
an asymptote. Okay.
Yeah, I just want to make sure.
Yeah, I missed it there. So point where it crosses is -1.1, and this point is -2. Okay.
So, thank you for the wonderful lesson.
Okay, so this is for you to try.
You saw him in a good time?
Okay, find the linearization of 2 raised x.
Y equals to 2 raised x. So what we're going to do at the very least is
In the neighborhood of a equals 0.
So what we're going to do at the very least is f of a. X is going to.
So if y is 2 raised x, this is any base other than b. So if you recall, we found the derivative of y raised, excuse me, b raised x. Which was simply b raised x multiplied by ln of 2. Excuse me, ln of b. Yes, so in our case, we have b to be 2. So the derivative would simply be 2 raised x multiplied by ln of 2. So the original function is f of x. And that would be f prime of x. Now we simply have to find a linearization. So in the neighborhood of a equals 0, so plug in 0, 0, 0, L of x would be equal to f prime of 0 times x minus 0 plus f of 0. What do we get when we plug in 0 in the derivative? 2 raised 0 times ln of 2, just ln of 2. Plug in 0 in the original function, I get 1. So that is the linearization of the function in the neighborhood of 0. Of course, I plug in 0, I am going to get the actual value of the function, which is 1. If I plug in 1, what is the value of the function at 1? 2. Now, use the approximation, we would have ln of 2 times 1. ln of 2 is 0.69. So I'd end up having 1 plus 0.69. So at 1, the actual value of the function is 2. The approximation will be 1.69.
Wait, why are we using 1? Wouldn't we use 0.01 positive and then negative 0.01?
I'm just trying to explain that your target, you go from 0 to the worst going to get. So instead of going to 0.05, negative 0.05, I jump to 1 so that I go far away from 0.
So I know that you talked about this in the beginning, but you're basically just taking the original function and derivative and trying to figure out the rate of changes approximately or a point.
Yes.
Okay, on that line.
Yeah,
All right.
on the curve.
On the curve, okay.
So if you draw this curve, this is an exponential curve. Yes, so that is the nature of the curve. When x is equal to 0, I have 1. When x is equal to 1, I have 2. Yes, but in this case, if you draw a tangent line, would the tangent line go above the curve or below the curve? Below.
And why is it below again?
The curve's going this way.
Okay. Oh, yeah, never mind.
Because this is a good lead into chapter 4.
Yeah.
Because we would encounter something called concavity. So if it's open upward, concave up, you're going to have an underestimate. That's concave down, you would have an overestimate. Naturally, the value that the tangent line estimated was 1.69. Is 1.69 below 2? Yes.
And how does this come into play when we're approximating the area under the curve? Does this like play into that once we get there?
Oh, that's integrals.
No, I know, I was talking to my buddy about it today, because that's what he's working on right now.
Yeah, slowly, I mean, not slowly, slightly different from the content, but very close.
Very close.
I'll explain when we get to that.
All right, sounds good.
Do we add the 1 to the ln to the top 2? So why didn't we do the same thing with
There's so much. So last time we had 16x plus 23.
Yeah.
Yes. So we plugged in values here and we added 23 to it. Right. In this case, instead of 16, I had ln of 2. Instead of 23, I have 1. But still, I have a line.
But why are we adding 1 like,
Because if I evaluate
Oh.
1, I would be 1 plus ln of 2.
so are we evaluating, we're not adding it before? So it
Yes.
doesn't really.
Yeah, it doesn't matter.
My son,